Asking the impossible, the Big Bang is often described as the beginning of everything, of space, time, matter, and energy. It's the cosmic drumbeat that launched the universe we see today. Yet even as we trace the galaxies racing apart, the background radiation still humming from those early moments, and the abundance of hydrogen and helium forged in the fires of the first seconds, a deeper question lingers. What came before? At first glance, it seems like a natural question, as intuitive as asking what lies beyond the horizon or what happened yesterday. But with the Big Bang, we quickly run into a problem. Time itself is thought to have begun with that event. There was no yesterday, no earlier moment ticking away. There may have been no ticking at all. Space and time are inseparable, at least in this universe, package pair, and asking what's before this universe, much like asking what's outside the universe, gets problematic and non-intuitive. In fact, the answer to both might be nothing. To ask what came before the Big Bang may be like asking what's north of the North Pole, a question that dissolves not because the answer is hidden from us, but because it has no meaning within the framework we understand. You can still go further up, or sideways, rising off the planet, but that's further north, just up, and similarly, even if there is more beyond or before this universe, it might be that time and space don't apply, same as left or right don't mean anything in the context of planetary directions like north, east, south, or west. Still, we are human, curious to the core, and ever defiant of boundaries, even those drawn by physics. So today, we'll explore the frontier beyond the frontier. We'll ask not only what could have come before the Big Bang but whether that question itself needs to be reimagined. And we'll tour the many scientific theories that attempt, each in their own way, to pull back the ultimate cosmic curtain. The limits of time and space-time in the earliest moments of the universe, so early that calling them moments already feels misleading, our current physics gives way. General relativity, which so beautifully describes the curvature of space-time, predicts a singularity, a point where densities and temperatures become infinite, and the laws of physics break down, much as they are thought to do at the center of black holes. But infinities are suspicious creatures. When they pop up in physical equations, it's usually a sign we're pushing a theory beyond its limits. Many physicists today argue that the singularity is not a physical reality, but a placeholder for where our understanding fails, and I tend to agree. More intriguingly, general relativity suggests that time itself is not a backdrop against which things happen, but a property that emerges with space-time. If space-time was born at the Big Bang, so too was time. Without space, without matter and energy to interact, what would the ticking of a clock even mean? This leads to ideas like the no-boundary proposal, developed by Stephen Hawking and James Hartle. Rather than a singular point where everything began, they envisioned the early universe as finite but without a boundary, much like the surface of a sphere has no edge. But there's a deeper twist. Near the Big Bang, time itself is thought to lose its familiar meaning. In Hawking and Hartle's model, the early universe can be described using imaginary time, where time behaves more like a spatial dimension. In everyday 3D space, we calculate distances using the Pythagorean theorem. The distance squared is the sum of the squares of the differences in the x, y, and z directions up down, left right, forward back. We move this into spacetime by having a spacetime interval, where time gets turned into a kind of distance, the causal distance being the time interval multiplied by the speed of light, how far light would travel in that period. We square this, but instead of adding it to the squares of the spatial distances up down, left right, forward back, we subtract it. That's the normal approach in special relativity, and it reflects how high relative velocities or strong gravities tend to either shrink distances or stretch out the local passage of time. In imaginary time, we take the time coordinate and multiply it by the imaginary unit, the square root of -1. When we square this, it flips the negative sign, effectively adding the time term instead of subtracting it. The result is a more familiar four-dimensional distance formula, where time and space are treated alike. That's why in imaginary time, time behaves more like a spatial dimension. It sounds technical and mysterious, probably because a lot of people explaining it seem to aim for that, but it's really not. Instead of flowing from past to future, in this framework, time becomes just another direction you can move through, indistinguishable from the directions of space. In this view, The universe near its beginning is shaped like a four-dimensional hypersphere, finite but unbounded, and the sharp distinction between time and space only emerges as the universe expands and cools. Effectively, four physical dimensions and no temporal one. So again, asking what came before the Big Bang then becomes as meaningless as asking what's north of the North Pole, but here, it's not a 3D sphere we're talking about, it's a 4D one, and there's no sharp corners or hole for a singularity. It's an elegant solution, replacing a problematic singularity with a softer, rounded start. But not everyone is satisfied. It may explain why time doesn't extend backward before the Big Bang, but it leaves open the deeper mystery of whether something more fundamental gave rise to spacetime itself, a mystery that theories of quantum gravity are still struggling to solve. Imaginary time is also used in Euclidean quantum gravity. We'll bypass discussing what a Wick rotation is and why it's handy in quantum, but the justification here is that we can maybe switch over to using imaginary time in the ultra-early universe because of how incredibly dense it was and how sharp the curvature of spacetime would be. In the earliest moments of the universe, the first force to emerge was gravity, and when it was doing that we were definitely in the realm of quantum gravity, due to the tiny space and massive energy scales, and we don't really understand quantum gravity yet and have many competing and less than compelling theories for that. You also have serious causality issues with using imaginary time, but at the beginning of time and at the quantum level, you pretty much have these anyway. So, again, elegant but does suffer from some big issues. You might be trying to figure out what imaginary time is in a physical context. If so, don't waste your time. The answer is it hasn't got one. Imaginary time is a mathematical method. There's no such thing as an imaginary second in the physical world. Imaginary numbers extend math beyond the real, but -1 still has no physical square root, and there is no imaginary second or year. Beyond the bang, alternate beginnings. If the Big Bang wasn't truly the beginning, what could have come before? In the search for answers, physicists have looked beyond the familiar landscape of particles and fields to more fundamental terrain where space and time themselves might not yet exist, or where they exist in radically different forms. Beyond the Big Bang, alternate beginnings, one of the earliest and most intriguing ideas comes from string theory. See our episode on string theory for a deeper dive of the topic. In this framework, the basic building blocks of reality aren't point-like particles but tiny, vibrating strings of energy. Each vibration mode corresponds to a different particle, much like the various notes a violin string can produce. But for the mathematics to work, string theory requires extra dimensions, beyond the three of space and one of time we experience. Enter string gas cosmology, an idea proposed by Gabriele Veneziano and colleagues. Here, the early universe wasn't a smooth, empty void, it was a dense, hot gas of strings. In this primordial state, space was tightly wound, compacted into tiny loops, perhaps as small as the Planck length, 10 to the power of -35 meters. Time, as we know it, didn't exist yet. Instead, the universe was in a kind of quasi-static equilibrium, a timeless sea of quantum chaos. Over time, if time even applied, some of the spatial dimensions began to expand while others remained curled up, giving rise to the four-dimensional spacetime we inhabit today. In this view, the Big Bang wasn't the beginning, it was a phase transition. And a potentially local one, our universe erupting from this wider ocean. Like water freezing into ice or steam condensing into water, the universe shifted from one state of existence to another. From a tangled thicket of vibrating strings emerged the smooth fabric of space-time. Other models in string theory paint an even grander picture. In pre-Big Bang cosmology, inspired by the works of Veneziano and others, the universe started in a state dominated by gravitational waves and dilatons, exotic fields predicted by string theory. Instead of a singularity, there's a mirror-symmetric bounce. The universe contracts in one phase and then smoothly transitions into expansion, flipping the arrow of time along the way. If such a bounce occurred, the universe could have an infinite past, a prehistory stretching backward forever, though with conditions so alien they defy easy description. Space and time, in their pre-Big Bang forms, might not resemble anything we recognize. Some even propose that our universe is but a bubble in a grander cosmic foam. Bubble nucleation is a feature of certain inflationary models, particularly eternal inflation, where the underlying vacuum, call it the more fundamental reality, is unstable and regions of it occasionally pop into lower energy states, forming new universes. Each of these bubbles expands, potentially colliding with others, creating a vast multiverse of pocket universes, each with its own laws of physics. If that's the case, the Big Bang we know and study was merely the local beginning of our bubble, not of existence itself. This leads to a tantalizing possibility: bubble collisions. If another bubble universe collided with ours early in its history, it could leave behind scars, subtle imprints in the cosmic microwave background, the faint afterglow of the Big Bang. Some scientists have searched for such patterns, circular anomalies, telltale disturbances that might whisper of ancient cosmic collisions. So far, nothing definitive has been found, but the search continues. And this is a very positive aspect of this particular theory, as most of our notions of time and space beyond or before our own universe tend to have no way for us to collect evidence of them, which is obviously problematic for science. We have many radical ideas about cosmology, many